applied scientist at Microsoft Research India. Prior to this, he was a senior scientist at Microsoft Gray Systems Lab in Madison, Wisconsin. His areas of research include query processing and optimization in large-scale databases and data management systems. He holds a PhD in computer science from IIT-Bombay, where his work focused on improving performance of database applications using techniques that lie in the intersection of databases and compilers of programming languages. His work has received an honorable mention for the 2015 ACM Sigma Jim Gray Doctoral Dissertation Award and has won the IIT Bombay Excellence in PhD Research Award. Prior to his PhD, Dr. Ramachandra spent 5 years at ThoughtWorks in INC, where he led team designing and developing enterprise software systems. Dr. Ramachandra will now speak on algebraic representation for imperative programs.
First of all, thanks to Srinivas, Vivek and all the organizers of RMIT for having me here. So far we have heard a lot of math related talks, and now I'll be taking a detour, and this will be more of a systems, like computer science systems, industry oriented talk. This is some work we've been doing for the last few years at Microsoft, and also partly I worked on this during my PhD a few years before. So just briefly go over the agenda. First I'll talk about the problem, which is about the contrast between declarative SQL. How many of you know SQL? Like even just simple, yeah. Okay. And imperative programs. By imperative programs, I mean programs that you write in languages like Python, Java, any programming language, standard programming language. And then I'll motivate it with an example. And then I'll talk more about UDFs and what's the good, bad, and ugly of them, and why this problem has not been addressed so far. And then I'll move on to the solution, give an overview, and do an experimental evaluation, which is part of our work, and then I'll conclude. All right, so there are few publications that describe this work over the years. I'll just list them here, but I mean just to get it out of the way. So this was some of the earlier work we did, and then more recently we have had like 3 publications around this, and this talk sort of summarizes the work over all these 3. So let me move to the problem, right? So this is a typical scenario where you may look at enterprises like Flipkart or Amazon or these huge retail or these kind of industries where they have databases like this, right? So they have customer data, which may run into millions or even billions, where they store customer information in a table. And then they also have orders, which is basically whatever you order on Flipkart or Amazon or whatever, right? So there are, for people who know databases, you know that this is a one-to-many relationship, where like one customer can have multiple orders. So there is a foreign key. I don't know if you can stop me if I'm saying something which you don't follow. So there is a foreign key to map this one-to-many relationship, so that there is a customer key in the orders table, right? Which will say that what are all the orders made by a particular customer. And there is other details about the order itself. Now there is a manager who heads a group of engineers, and there are 2 developers in the team. And one day she comes with a new requirement and says, we want to categorize our customers into 3 categories. This is more like a rewards sort of program, right? So you want to categorize customers into platinum, gold, and regular. How do you do that? So there's a simple logic to do this, simple algorithm. If the total orders made by a customer exceeds certain amount, you call them platinum customers. If it's in between like 5 and 10 lakhs, you call them gold, and otherwise they are regular customers. Right? It's a simple problem that she gives to the engineers. And it turns out that these 2 engineers seem to disagree in how they want to implement this. So they go about implementing it in their own way. So one of the developers happens to be an SQL expert, right? So he knows very good SQL, like how to write complex SQL queries and all that. So he writes one SQL query, which gives you this answer basically. Which just says that for every customer with the customer key, it will tell you whether that customer is a platinum, gold, or a regular customer. using some complicated SQL. Let's leave it at that. By doing a join, by basically computing the total number of total amount of all the orders and all that. So fine. So the other programmer, the other engineer doesn't know like complex SQL, but he's a good programmer. He knows Python, Java, all those sort of programs. So he decides to write it in a different way. He writes a simple SQL query which says select customer key and service level, which is basically what they're asking for from customer, and all the logic or all the behavior is implemented inside this function called a user-defined function in SQL. So that function looks like this, which takes in a customer key, right? And it basically executes a simple query to get all the sum of all the price of all the orders that customer has made. And then it uses a simple if-else logic to if-else branching, conditional branching construct to decide whether the customer is right. So both are valid ways to solve this problem. The programmer thinks that the way he's thinking about doing this is that UDF's the advantage of writing it this way is that it encourages modularity and code reuse. Like if somebody else wants to use this same service level in some other query or some other function somewhere else, they can just call this function and not worry about implementing it all over again. You don't have to duplicate it. And if the logic changes tomorrow, if they redefine this meaning of what a platinum customer is, they don't have to go and change multiple places and all that. So this is good software engineering practices, because of which it might be better to write it in the way on the right side. And it's also easier to read, right? I mean, for people to read and understand what's going on, probably the right side is more easy than this one. This one can be understood only by SQL experts.
So you said from customer is the name of a relation from which you extract all these columns over there.
Exactly. So a customer is a relation. Customer key is one of the attributes or a column. So again, orders is another table which has a column called total price. And it also has a foreign key to the customer table because there is a one-to-many relationship.
So the answer to a query is again going to be a relation?
Yes, yes. The result of this one is a relation with two columns. One is a customer key, and the other is this unnamed column here, which will just be which will say what the category of that customer is. Right? So some tasks are easier to express in this form rather than in a declarative SQL form, and it's some business rules can be coded better in this way and all that. So that's why this programmer decides to do this, and also because he doesn't know good SQL. Now they both come back to the manager with their respective solutions, right? And our programmer is hoping for a promotion because he thinks he has implemented it in a very using good software engineering practices and everything. But it turns out the manager says some things to these two. So the question to you is, one of them was promoted and one of them was fired. So whom do you think was promoted or given a raise, and who was fired in these two? Any? Sorry?
Database SQL expert is promoted.
Why is that? Why do you think?
I believe.
You should tell me why. Any other answers? Sorry? No, his answer was right, but the
code is more declarative. His code is more declarative.
Sure. So? Or what does that, what's the advantage of that? Or what would that give you? Which the imperative doesn't? Or, you're on the right track, yeah.
The imperative binds you to do things in a certain manner.
Exactly.
The declarative thing doesn't.
Yeah, very true, yeah. Yep. Okay, let me move on. So obviously, as you said, the programmer was fired, and the SQL expert was promoted. And the reason is, you gave the root cause of the reason, but the manager also doesn't know that. From a manager's point of view, what matters was that she basically ran both these programs on their millions of records, right? On their database of millions of customers. She ran both of these, and this one ran within around 2 minutes. It completed for all the millions of customers. It was able to derive whether who was platinum, etc. Whereas this one took a few hours to run. Now this was unacceptable for whatever reasons. from a business sense, they wanted the solution to be more performant. And this order of magnitude difference is not acceptable in industry in many cases. So that was the consequence. But the cause why this was slow and why this was fast was because of what you said, which is that this is a declarative form which is amenable to alternative ways of implementing it, or more efficient ways of implementing it, whereas this one binds you to implementing it in a certain way. I'll go into more details of that. That's basically the premise of my talk, is that the benefits of UDFs. So there are a lot of benefits of using it this way, right? Like I said, all the software engineering benefits are there, but it comes with a huge performance penalty today. You can try this on any database. This is not specific to any particular implementation or anything. This is a conceptual performance penalty. So let me move on to the problem of why UDFs or these such functions are perform really badly. First of all, in databases, an SQL query goes through what is called as a query optimization phase, and then the query execution. Query optimization is where the query optimizer basically looks at different alternatives to execute that query, right? So, for example, if you have a join between two relations, you could implement it using a nested loops join, or you can do it using a hash table, using a hash-based join, or if they are already sorted, you can do what is a sort merge join. So there are different algorithms which may be efficient depending upon the kind of the data and so on. So the optimizer makes this cost-based decision. So it is a cost-based optimizer which is at the heart of these databases. So it turns out that databases, the query optimizers, do not look inside UDFs at all today. The query optimizer treats such UDFs as black boxes, and do not look inside what's going on and how to cost them, right? So they don't know how to associate a cost, like how expensive is it to evaluate this function. So it's not very easy to build that cost model, but whether it's easy or difficult is different, but the fact is that nobody does it today. And not only that, it becomes harder to parallelize. So when it comes to executing such queries, you may be able to run them on multiple cores and gain the benefits of parallelism. But it turns out when there are functions like this, there are limitations which makes it harder to parallelize. And then these functions happen to be interpreted, like statement by statement, versus compiled into a single expression tree or something. So there are no cross-statement optimizations. A compiler does a lot of things like dead code elimination, constant folding, propagation. I don't know if there are several compiler optimization techniques which can't be applied here because this is interpreted. So it turns out that whenever there are UDFs in a select clause, like I said, like this, there is a select clause, or even in the where clause. So here what is happening is for every tuple in the customer relation, for every row, it is calling this function, right? So this is called as the iterative execution of the UDF. So you're basically calling into a function for every tuple. So that is very inefficient, because also there is a function call overheads, and there are a lot of things that are bad, I think. So but why have people not tried to solve this or address this problem yet? It turns out, so the database community, people in the database world where I come from mostly, they have focused on optimizing declarative SQL. If you write a query like I showed the SQL expert had written, even though that may run into hundreds of lines of code, if the query is very complex, query optimizers do a great job of simplifying and doing all the algebraic transformations and they apply all the relational algebra rules and things like that to optimize those. But that has been the focus. They have not focused on these imperative programs or UDFs. And there are no benchmarks. So the industry investments in these improvements are all driven by benchmarks. They want to compete with each other, saying we perform better than some competitor on this benchmark and things like that. So it turns out the benchmarks don't have UDFs in them, so they don't bother about it. And it's also hard. This problem is not very easy because there is what I call as imperative versus relational impedance mismatch. So there is a relational or a declarative way of talking to a database, and there is this imperative way. They are two sort of complementary ways, but there is a mismatch. If you try to combine them, it's not clear what's the best way to come up with an efficient way to evaluate such programs, which have a mix of imperative programs and code and declarative queries. So there is this sort of has an interdisciplinary angle to it because there is some compilers angle and classic query optimization angle. And I'll show later in the talk that you can always say that there are compiler people have already they have come up with a lot of work. There's been decades of research into how to optimize such programs. Why can't you just implement those and be done? It turns out that's not sufficient. In this case, I'll show why later. So what do people do in the wild, in the industry? They just hire DBAs. DBAs are paid very heavily, database administrators, to do tuning, and they know the problem pitfalls of using UDFs, and they try to avoid it and so on. So that's how people are working around the problem, but there has been no solution. So before moving on to the solution now, so I'll move on to how we try to address this problem. I'll just give a brief one slide introduction to relational algebra, just for the purpose of following the rest of the talk. So like any other algebra, the relational algebra operates on the set that is under consideration is a set of relations, or more popularly called as tables. And then there are a bunch of operations on these relations, right? These operations can be, there's some examples here, unary operators like selection, which basically filters some rows from a relation and gives out another relation. Projection, which filters or removes some columns and gives out another relation, right? And rename, which basically just a logical operation to rename the attributes. These are just examples. There are more, of course. These are some of the common ones. Binary operations, like a cross product. You can do a cross product on two relations. A natural join, which is basically based on a key. You do a join of two relations. And then there are variants like left outer join, right outer join, and so on. If you have taken the undergraduate database course, you would be aware of these basic operations. And there are also these aggregate operations like group by, which allow you to reduce, they are row reduction type operators, which sort of aggregates multiple rows into a single row and so on. So as a simple example, if you give a query like this, which we had used earlier, in relational algebra, you would write it like this. So this is from the customer relation. You are projecting out two columns. One is the customer key and the other is the function here, right? This is a simple relational algebra expression for this query. So that's with that, I'll just describe the overview of our solution. It's based on two observations. So first of all, iterative execution of UDFs. Like I said, we currently execute UDFs iteratively. Like for every tuple, you call the function, right? So that is similar to execution of subqueries. So let me give an example. So this is a query with a nested subquery. So the blue part is actually a nested subquery. So what this is doing is, from the part supplier table, it is trying to select two columns where the supply cost is the minimum supply cost for a particular part. So again, it's like a self-join. Basically, this is also on the same table. But what we are doing is we are trying to get the minimum supply cost for a particular part, and we want to select the supplier who supplies the part with that minimum price. So basically, at a high level, this is just a subquery, a query with a subquery in it. So how do you evaluate this? One way to evaluate or implement this query is, for every tuple in the green part, you evaluate this using this p1.part key. P1 is from outside, right? So there is a correlation from the outside query. So you can evaluate this blue part once for every tuple in the green query. Is that clear? So it's almost like a for loop. You can say, for every tuple here, compute the minimum cost, then do this comparison and move on. So that is how we are evaluating UDFs today, essentially, instead of if you think of this as a UDF instead of a query. But it turns out that RDBMSs, or like databases, are very good at optimizing these kind of queries already. So there has been a lot of decades of research that has gone into how do you efficiently implement these kind of complex queries with subqueries. For example, one of the work which we rely upon here is that correlated subqueries. These are correlated because there is a P1 inside the subquery. So there is a correlation between the outer and the inner query. So correlated subqueries like this can be modeled using a new relational operator called the apply. It's no longer new, but of course it's widely used, but called the apply operator. And basically the apply operator evaluates a parameterized, okay, let me give this, you look at this equation, right? So this is the apply operator. Ignore the operator on top of that. But so if it takes two inputs, E0 and E1, and the way it is defined is E0 apply E1 is basically for every tuple in E0 in the left child or one of the child, you take that tuple and the right side E1 is basically a parameterized expression in terms of T, which is from the left side. So for every tuple on the left side, you evaluate the right subtree of the apply or the right child, and then you perform a join operation. So this operator is a join type, which can be any join operator like cross product, left outer join, and so on. So this is in essence a parameterized join operator you can think of, where one side of the join is parameterized by the other side. So the relational expression tree for this query will look like this, where so there is an apply cross here, where for every tuple on the left side, you're basically saying you do this, you evaluate this. So this right child is parameterized by this P1.part key, which is basically coming from the left side. So you can model correlated execution using this apply operator. Now all we have done is just model it into a tree by introducing an operator. How does this help? So once you model this, there are these transformation rules which people have come up with over the years, which can replace apply with standard relational operators like join and others. Thereby what happens is it ends up doing decorrelating, or what I mean is that there won't be any correlation anymore. For example, this was the tree I showed in the previous slide. This is correlated execution modeled using apply. And what will happen in today's query optimizers is it will transform it into a tree like this. Now the right side is equivalent to this, but if you see, the right side is no longer parameterized by this left side here. This is a set oriented, it's just doing a group by on part key and computing the min for every part as one set oriented operation, and directly performs a join and performs this filter. So it's a very interesting, I mean, I won't go into the details of how these things are there. There are several rules like this which can transform this correlated execution into a decorrelated plan, which is set oriented or which is vectorizable or which can be executed in parallel instead of for every tuple type of semantics. So our main intuition is that the same idea what people have built for subqueries can be extended for arbitrary imperative user-defined functions. So that forms the main intuition. So so the crux of the problem is now that if an entire imperative UDF, like the function that I showed, the service level function that I showed, if you can express that entire function as one relational algebra expression, then you can treat that as a subquery. And once you treat that as a subquery, you can leverage all the subquery optimization work that has been already done. So the question is, how to take a UDF which could have complex if-else and variables and all that and express it as a single SQL query or a single relational expression, right? So that's what we'll move on to now. So I'll go through an example, our example, and show how we do it. I won't go into the proofs and the details again, but this should give you an intuition of how this works. So for every imperative construct, like a variable assignment or a conditional branching and so on, we have a equivalent relational algebra expression. For example, there was this statement called set level equal to platinum, right? So this is a simple variable assignment. You can think of it in relational algebra on the right side. You can think of this as you are projecting from so S is basically a dummy relation or a relation that just gives out an empty row with an empty, like basically it's like an empty relation you can think of. So all we are saying is that you can project out a constant projection with value platinum and give it a name, alias called level. So which is in SQL you would write it like this: select platinum as level, which is basically It's like a one row, one column table at this point, where the column name is the variable name, and the value is the value of the variable at that point. So this is a logical, just a logical representation. This won't be in when it executes. This won't happen. But so this is a one way to represent a variable assignment in relational algebra. Similarly, now you have a statement where you're assigning. This is also a variable assignment, but on the right side you have a query. Right. So you're selecting, you're assigning V to be the sum of the total price for whatever, for some orders. So again, you can use the same thing. You put this, the right hand side becomes like a subquery, and then you project it as a column. So again, in relational algebra, I'm just projecting a column V, which is basically a sum of total price from orders where customer key is equal to that key. So now this becomes a relational expression for a statement like this, right? Similarly, for a conditional branching statement like this, we can write it using there is a case expression, which is also a projection, but it's a conditional projection, like a ternary operator type thing. I don't have that here, but basically in SQL you can represent it using the case expression, right? So now we have shown that for individual statements there is a mapping already. This is not something we have to define. But now the challenge is, of course, yeah, I'm showing it here in SQL for only readability or for us to understand during the presentation. All these transformations happen on the relational algebra tree in our implementation. So now we come to our function. I've simplified it to have only 2 levels for lack of space. There's only platinum or regular. Now what we do is we take these basic blocks, or what we call program regions, which are structured blocks in a program. These are commonly used in the compiler's world. We take these blocks and we come up with relational expressions at a block level. How do I do that? So now in this block there are 2 variables that are being written to or declared. One is the total and one is level. So I have like this basically is a 2 column 1 row table at this point, where the level variable is still null and total variable has the value of the total price. So you can logically think of it as a single row 2 column table with the values of those variables that are defined in this block. So similarly you can do the same thing for the next block, but you should notice that, so here I'm using the variable total, which was defined in the previous. So there is a alias that I can give for these relations. These are called derived tables. Again, these are not new. These are all used already. So you can use you can alias it using things like dt1.total. So you can refer to the previous value of a variable using this. So this is how we can preserve data flow dependencies, and that is key to maintaining the semantics of this UDF even while transforming it into a relational expression. Similarly, for the else block, you have another. Notice I'm using dt1 and dt2 here. And then I'll come to this. So essentially what happens is, for every region, so this is region 1, 2, 3 and 4, every region I have one expression at this point, right? So now what I do is, when I have a return of a particular variable, all I do is I add a projection on that level. Sorry, this should be R4, not R3. That's a typo. So this is expression for R1, which is this. Apply cross, I'll get to that. Expressions for R2 and expression for R3. So now, so like I said, this is the expression for R1, which has these 2 variables. This is for R2, which has only 1 variable. And then you combine these expressions using the apply operator. So that's where we make use of the apply.
Creating new relations for every region, essentially.
You can logically, yeah, not I mean, it won't be materialized, or it's not something that, right. This is just for algebraic simplification. This will get simplified. I'll show you how. But
the regions themselves, how do you identify?
That's a standard static analysis. You can, if you go through abstract the syntax tree and you build a control flow graph of this UDF, which compilers do for all the optimizations, right? So you can come up with, like, you can extract regions from a program based on their control flow constructs and the control flow graph.
Straight line portions of it.
Yeah, all the straight line portions become basic blocks or one kind of region, and this whole if-else region becomes, so this is actually a nested hierarchy actually. So this whole thing is a region which is composed of a few other regions, and this I've simplified it here. Actually, the set itself is a small region, which is a single basic block of just this one statement, and so on. So you can build it in a hierarchical way, and yeah, that's a standard technique. So now the nice thing about apply is that, like I had said earlier, if you want to, in this expression, if you want to use the value of a previously computed expression, you can apply will provide you that semantics by using this correlated evaluation semantics. So you are saying that for every tuple here, these are single tuples, mind you. So these are, if you do a cross product, you are still getting a single tuple. So the value of this variable will be available for the right side to use for computing its expression and so on. So, and at the end, we basically project out the column that is of interest, which is the value that is returned by the function. So now you can see that this whole thing is just a single relational algebra expression. If you come back to this is how it will look like as a complex SQL query now. So this left-hand side is equivalent to the right side here, but the left side is an imperative function, but the right side is one SQL query, although more complex for a human. It turns out it's not complex for a query optimizer. So once we do this, again, there are some simplifications that I have not gone into all the details here, but you get the idea. So now all we do is we take this query, and at the place where there was a function call, you replace that with this humongous query that we built, or the relational algebra expression that we built, and you just substitute it and then leave it to the optimizer to figure out what to do next. So it turns out the optimizer is pretty smart. Like what it does is, this is sort of a high-level view of what are the simplifications it would do. So this was the input relational expression, and we basically replaced this function call with this expression, right? Which is basically the expression for R1 apply R2 apply R3, which is the complex SQL query. So there are these transformation rules for apply, like the one I showed you earlier. There are several others. I won't go into the details, but you can those things get applied as their preconditions match and so on. And finally, we get an expression that looks like this. So projection of customer key, and this is the conditional projection as V from T3, where T3 is another query, is a subquery basically, which is saying customer left outer join orders and group by customer key and compute the sum of total price. So basically, this whole thing is now a single query, which is after simplification. So if I take this query and try to rewrite it in SQL, this is what it will look like. So basically, the optimizer has translated what we gave into something like this, which is very similar to what our SQL expert had manually written. Right? So, but now we are able to achieve it, automate this whole process by using by being able to compose this or transform this into this whole apply-based expression tree, and giving it to the optimizer to come up with this. So the interesting points about this right side, about what has happened here is that here, if you see, there is actually a join. So for every customer, right, for every tuple in customer, we are calling the function. And this function is doing a lookup on orders by that customer. So this is essentially a join between customer and orders based on customer key. But in this form, it is not explicit that it is a join, and it can be implemented using nested loops or hash join, or you could do different tricks to efficiently run this join. But that is hidden here, that is implicit. But the optimizer has now made it open, right? So now it can see what's going on inside. So it's able to decipher that there is a left outer join happening here, and also there is a group by, because you're doing a sum of total price per customer. So that is basically group by customer key. You are doing computing the total price. You want the total price of orders made by a particular customer. So the implicit relational operations here, both join and group by, are made explicit. And this is an example of what a compiler will not do. So even if I implement all compiler optimizations on this function to do dead code elimination and constant folding and propagation and all that, it will not be able to infer that there is a relational operation such as a join happening here. That's why we need something more than what compilers can do today. And then the other advantage is the operations inside the UDF are now costed. I mean, the optimizer knows how to cost these operations now that they're all open, right? They're not inside the black box, which it used to be. And then this plan is parallelizable. This join can be implemented in a parallel way, and whatever. The optimizer is free to use parallelism. And then there is no function call overheads, right? So here there is a context switch happening for every tuple in the customer, whereas here there is no such thing. And then the beautiful thing here is that from an industry point of view, this required no changes to the query optimizer itself. We changed the input to the optimizer, right? So we just take the input used to be this, and this was a black box. We transformed this into something that the optimizer can understand and gave it to the optimizer. So from an industry point of view, changing a query optimizer which has been in production for decades is very risky. I mean, if you cause some other bugs which unrelated to your improvement and all that, you may be hampering businesses of several customers who are running mission critical workloads and so on. So people are hesitant to make intrusive changes to these core parts of a database engine. But the advantage of this technique is that you don't have to change the optimizer itself. So now our programmer is also promoted, just to conclude that story, because what he wrote also ends up running in the same time as the SQL expert. So all we are trying to say is that even if you're not an SQL expert, you should be able to use databases and get the benefits of databases, even if you are expressing your logic in a different way. So there is not only a promotion, but there is a bonus. Yeah. Yeah. So yeah, I didn't show. I mean, that gets more complex. So we have an implementation, or we have an approach for loops, which are cursor loops, which are primarily loops over relations. That's easier to algebraize or convert into a relational algebra expression. But there are these other arbitrary loops, like while I less than 100, I is equal to I plus 50, whatever. I mean, or you could have some complex such. Those are harder to express as a single relational expression, but we have some, that's sort of work in progress. We have some ways to, we can use, there are techniques like loop fission and so on from the compiler's world, where you can split the loop into two and build up a relation of, or build up a relation of all the values for iterating over and convert an arbitrary loop into a cursor loop and so on. So, but that is work in progress. But yeah, you're right. That is one of the hard aspects of this. So there is, like I said, there is not only a promotion, but there is a bonus of getting compiler optimizations for free. I'll run through this example quickly. This is a toy example, which basically takes a variable, and if the variable is greater than 1000, it says value equal to high, otherwise low, and just returns a concatenation of high value or low value, basically. Now, given this function, what a compiler would do on it today. So suppose you call this function for getVal of 5000, which is a constant value, right? So if you call this function on a constant like this, it does what is called as dynamic slicing, which is basically compute the slice of the program which is valid for this input. So it can basically evaluate this predicate x greater than 1000 at compile time, and realize that all I need is the true branch of the if condition, and the false branch is never taken for this particular call. So it can remove the if else and replace it with a single straight line code like this. This is a slice of this program for a particular input. And then you can apply constant propagation and folding here, because the value of the variable val is a constant at compile time. So you can actually take that and apply, substitute it here where it is used. So you are basically, and you can fold it. This string append is also, both are constants. Both the operands of the append are constants at compile time. So you can compute this at compile time, not wait for runtime. So you can, this is the output of constant propagation and folding. And after that, you realize that the first two statements are dead code now, because this variable val is never used. So this will get simplified into a single statement like this. This is what a compiler will do today. Let's see what we do. Basically, we are taking this function and we translate it into something like this. I won't go into the details, but using operator. And there are some simplifications that naturally kick in when you express this thing using an apply, which I will skip the details, but it will also result in the same simplification. So without any additional effort, we get the benefits of all these compiler optimizations also on UDFs. So that's the key takeaway from this slide. So moving on to some implementation evaluation, I'll wind up soon. So we support this whole bunch of constructs. Like I've not mentioned loops here deliberately because it is work in progress, but we support all these very commonly used constructs in imperative programs. And we have evaluated it on our customer workloads at Microsoft, as well as some benchmarks which we have modified to include UDFs and so on. This is a machine configuration on which we have run some of our experiments. And we also did some analysis on Azure, which is our cloud database offering, right? So where we can host databases on the cloud. So we looked at out of the millions of databases that are hosted on the cloud, and out of those, all the UDFs that are defined in those databases, how many of them will be benefited by this technique? How many of them can be optimized using what we have today? So it turns out that we were able to do about 60% of those, which is a very big number for if we are able to improve the performance of 60% of the UDFs in the wild. That's a huge win for the product. So for a more detailed analysis, we looked at 3 customer workloads, which were of course taken from their permission with an NDA and so on. They had these many UDFs in them. Workload 1 had 178 and so on. We were able to inline. I mean, we call this transformation as inlining, although this is not necessarily inlining, but it's like an inlining of the UDF into the query. So yeah, so we see that we are able to inline a large fraction of UDFs in the wild. So just some performance numbers to give an idea. So the x-axis shows the number of the size of the table. So it decides. So the size of the table decides the number of times the UDF is called within a query. Like I said, right? For every tuple in customer, you're calling the function. If the customer table has only 10 rows, it doesn't matter whether you optimize it or not because it's a very small number. But the differences will show when you have large data. And the y-axis shows the time taken to run this. This is the kind of query. Select some function from table T, where size of the table is this, is the x-axis. So this is with inlining off, or basically without our optimization. You can see that this is like in log scale, this is linear. So which means it's sort of, yeah, it's basically, and this is also log scale. So basically the performance degrades linearly as the size of the table or the number of UDF calls within a query increase. So this is inlining on, but with the parallelism turned off. So we wanted to see how much is the benefit due to parallelism and how much is it due to this transformations of the apply operator and so on. So you can see that there are at a higher orders there are of the cardinalities of the table, there are like up to 2 orders of magnitude improvement in performance. And even at smaller cardinalities, we start to see benefits. And when we enable parallelism, it turns out that we get another additional order of magnitude improvement. I mean, the time taken reduces by another order of magnitude, only at higher cardinalities, because this is primarily because the cost-based query optimizer in a database decides whether to use parallelism or not. And that decision is also based on how big the data is, or the underlying data is, because there are some overheads to doing things in parallel. So it thinks that up to around 10,000 rows, it's not worth using parallelism. The overheads are more than the benefits. But after some point, it switches to using a parallel plan, which is why you see this this switch at later. And yeah, this is another benchmark which we just to give a overall execution time metric. So I'm showing 6 queries here from a benchmark. So this is the time taken as it without any changes to the queries in the benchmark. So we took some queries and rewrote some logic using UDFs, and by doing that, the performance went bad. I mean, it got degraded very badly. So the second bar shows how bad it got by using UDFs as opposed to not using it. And the third bar shows with UDFs and with our inlining, we can get back what the original So basically this says that there is no overheads to using UDFs anymore, whereas earlier the overheads were pretty bad. So again, I'll probably skip this. I'm probably running out of time. This is again a factor of improvement over the entire workload. We get like up to orders of magnitude improvement. So it's like a huge, which is not very surprising, because we are sort of getting the benefits of a lot of optimizations going together into this. Not only execution time, but also in the resource consumption, there is a benefit. So again, I'll move fast. So in summary, what we have built is extensible in terms of the constructs or the language that you can support, and language agnostic in the sense that we have done it now for this procedural SQL, but you can think of doing this for Python or Java or any language, because at the end of the day, all that matters is those constructs, that variable assignments and if conditional branching, they are the same in any language. So it's a language agnostic framework for representing and optimizing imperative functions in a relational database using relational algebra. So we have a technique to transform entire UDFs into SQL, a form that a query optimizer can understand and optimize. So then we make use of existing research in subquery optimization to get efficient plans and also get compiler optimizations, basically allowing users to get promotions easier even if they are not SQL experts. So with that, I conclude. So before taking questions, we are hiring if you are interested. Being an industry talk, I have to say this. So yeah, we are looking for interns, full-time research fellows, postdocs. So if you're interested, not just in the area that I spoke about, MSR works on a lot of interesting aspects of computer science, including theory. So if you're interested, yeah, you can reach out to me or anybody else in our lab. Yeah, thank you. So with that, I can take some questions.
So someday can we expect UDF to execute faster than relational DBMS?
Faster than relational, I don't know.
SQL?
I can imagine it to be on par. But yeah, what do you mean by faster? So then that means that you can also include those optimizations in a SQL optimizer, perhaps. So yeah, I guess these are just two ways of expressing intent by programmers, and that's how we have to look at it. So databases, in my opinion, have been very narrow-minded and said that you talk to me in SQL and then I can do good things for you. But we want to say that even if you can talk in other languages, we can understand you. That's sort of the, yeah.
If I'm not wrong, there are translators available which take imperative programming languages, translate them into declarative languages. This area is already there. For example, generating ML code out of C, C++ code and so on. Would it help you if you use one of these existing off-the-shelf translators and then do one declarative program written in one of the, let's say, logic programming language or functional programming languages, and then use that as an input to your translator and translate that into relational ways?
I'm not sure I fully understand your question, but
what I mean to say is you are taking declarative code as input and relational as output.
yeah.
I was suggesting if you could add one stage in between,
Yeah.
where you use an off-the-shelf translator from imperative to declarative, a logic programming language or functional programming language.
Okay.
And from that to relational.
Yeah, there are some, so we have used actually, in one of the other publications that I showed earlier, there are ways where you can try to transform this imperative. In essence, this apply operator is a functional notion of like a map style operator. So where you map a function onto a relation type of a thing. But I see your point. So you can have an intermediate representation which can probably cater to, we can sort of leverage some other languages and other translators. Yeah, definitely, we can do that. Yeah. Any other questions?
How much SQL is expressive? It is equivalent expressive as compared to imperative language. Whatever we can express in imperative language can be expressed in
Yeah, so if you are asking Turing completeness, standard SQL is not Turing complete, but there are some recursive extensions to SQL. So with those extensions included, it is Turing complete. So you can express any program in SQL.
Given any UTF, you will be able to convert it to, or for some you cannot be able to.
Yeah, right now, as I said, we cannot do everything. Like loops was an example he gave. We can only transform some kinds of loops, but not all. Yeah, conceptually theoretically it is possible to do everything, but practically we are not near at that point. Yeah.
Theoretically it is possible.
Yes, it should be possible. Or there is no, yeah, I mean, I don't want to commit or anything, but yeah, there is no reason why it should not be theoretically. Okay. Thank you.